Okay, so this is part 2 of the final exam study guide, questions 16 through 30. Um, let's get started. So, 16 asks what is similar between rubidium and any of these other elements. Well, we look at rubidium, and we know that it's in the first column. We know that therefore, because it's in the first column, it has some kind of ns1 valence shell electrons, which means, and remember this valence shell electron, that's going to determine the chemical and physical properties, aka the bonding patterns. Like what is it going to bond to, what is it not going to bond to? That all depends on ns1. So rubidium's in the first column. Looking at those other elements, potassium is also in the first column. Therefore, potassium will have a similar bonding pattern. Letter E. 17. Atomic radius. Now remember, if we look at our periodic table, atomic radius increases going this way and increases going this way, from right to left and up to down. So this is where it increases. So things, little increases here. So down here, this is our biggest and this is our smallest. Looking at our options, D is the correct answer. (18) Valence. What is the Lewis structure of oxygen? Well, oxygen has a, look at our valence shell electrons. We had said 2s2, 2p4. It's a total of 6 valence shell electrons. 1, 2, 3, 4, 5, 6. That leaves us with 2 unpaired. Right, 1 here, 1 there. Answer D. 19. Lewis structure of chlorine. Well, chlorine, sorry, got ahead of myself. Chlorine has a valence shell configuration of 3s2, 3p5 for a total of 7 valence shell electrons. 1, 2, 3, 4, 5, 6, 7. Awesome. It needs one more to be 8. And remember, 8 is stable. So put that other one right here. That was the extra, so it needs one more. The answer is C. 20. Difference in bondings. We know that covalent bonds are between a nonmetal and a nonmetal, and then ionic bonds are between metal, metal and a nonmetal. So with that in mind, we have to remember that staircase that as it separates nonmetals and metals. And the answer, I believe, is B. Sorry. 21. The polarity and electronegativity. So remember, polar is going to be the same. We're going to refer to our electronegativity. And electronegativity is pulling electrons in. That is electronegativity. It pulls in electrons. So when we look at our periodic table, something that looks like this, we know that electronegativity increases this way. So things like fluorine are the most electronegative, while things down here like cesium aren't. So when it comes to fluorine and hydrogen, fluorine has a lot of electronegativity, 7 valence shell electrons, and needs one more to be stable. It's going to pull the electrons over almost to the point of an ionic bond. Therefore, our dipole goes this way because this is where this, let me just highlight it for you. This electron right here will be pulled that direction because fluorine is so electronegative. That way, and we know that because of our electronegativity table. That's what makes it the most electronegative. So our answer for this one, E. 22. 22 and 23 are about the same. We're looking at which ones are most electronegative. Remember, if we look at 4 elements in the periodic table, this is our key. So for answer 22, it's carbon, which is C. Answer 23 is boron, which is B. Interesting. I don't know if I did that on purpose or not. 24. Almost done. The Lewis structure of CO3 2-. Now we have some steps for Lewis structures. 1, we have to count out the valence shell electrons for all of them. 2, we go single bonds, and then double bonds, and then triple bonds. We're trying to make the central atom an octet. And then we're going to use the extra electrons to fill in. So if we have C, we know it has 4 valence electrons. We know oxygen has 6 in that pattern. Here we go. So first thing I need to do is make, here's all my extra electrons. I'm going to put a couple up here. These are my extras. I'll make them little triangles. So first off, carbon needs to make some bonds. So first we'll go with single bonds. Single, single, single. Now I still have one left over on carbon, this one on top. There's going to be the double bond right there. Now at this point, I'm going to redraw it, so to kind of keep my sanity and keep. Here, let me just draw it down here. A carbon, and I had a double bond here with the oxygen, and it had a full shell. Then we had a single, 2 single bonds, each to oxygens. And then we had those 2 triangles. These are the 2 extra ones that go right there with that lone pair, that lone electron that we had. Now we have everything paired. Here's our CO3 2- Lewis structure. And just a little bit extra credit. This is a trigonal planar geometry because we make this fancy triangle. Trigonal planar. Triangle in the same plane. Cool. Oh, the answer. The answer is B. Let's see, 25. What is the Lewis structure of CF3? So when we refer to these geometries, we always want to check the Lewis structure. That will guide us through what we're trying to find. But we need to remember something. These are halogens. That last column before the noble gases, which means they're super reactive in all instances, and they will expand the octet. Gotta remember that. Halogens, reactive, and they expand the octet. So we start with chlorine. It's going to be our central atom. It has 7 valence electrons. We add some fluorine, It also has 7 valence electrons. It makes my single bonds. Single bond here, single bond here, single bond here. Now I notice that I have everything bonded, but I've expanded the octet around chlorine, and these two lone pairs are going to be in their own electron cloud. There's bubbles. So I'm going to redraw this in a little bit more specific geometry. Chlorine is going to have those two balloons, and they're going to repel themselves the most that they can, pushing all the way apart from each other, 180 degrees away from each other. That forces the fluorines to be in a special formation, one that goes out here with its valence shell electrons, one that goes towards you, that's drawn with a triangle filled in, that's towards you out of the screen in a different angle, and then we have this guy that goes back here, all their valence shells. Now when we look at the geometry of our, the idea is that these, let me draw this in red, these lone pairs are pushing away because they're repelling. They're very negative, and they're pushing everything in the same plane. So the F's are all in the same plane, in one big triangle, hint, hint, all in the same plane. And then we have this pyramid shape on top and on bottom. I'll put that in green. So we have this is on top, and then we also have this thing on bottom. I'll put that in purple. No, I already used purple. How about silver? Gray. I'll put this triangle on top. So I have this, so what I end up having is this one triangle. So I have like this weird triangle, and then it has a pyramid on top and a pyramid on bottom. So think about that. Two pyramids connected. This is trigonal bipyramidal. Wow, pyramid, did not spell that right. Trigonal bipyramidal. And just so we can draw this in a little bit better terms, I'll put it over here. Chlorine, fluorine. This is how it should look on your Lewis structure. Something like that. And now if you want to put these lone pairs out here too, that's definitely acceptable. Trigonal bipyramidal. Awesome. (26) Vesper. What does Vesper mean to you? Well, to me, it means that the electron domains repel each other. That's what it means to me. And I know that because opposites attract, and then the same repel. Opposite charges attract, the same charges repel. I know that each electron cloud is negative, and it's going to repel another electron cloud that's negative. That is Vesper. It's like the balloons that push each other away. Answer A. 27. CS2. Well, carbon has 4 valence electrons. Sulfur has 6. And then another sulfur has 6. Now watch what I'm going to do. First I'm going to do my single bonds. And then I'm going to do some double bonds. So here's another double bond. And this one over here is going to bond this one all the way over there. still a double bond. So when I redraw this, it's sulfur double bonded to carbon, double bonded to sulfur. Carbon has a full octet, sulfur has a full octet. I'm good. Now this is a linear pattern because it's in a line. Awesome. 28. Carbon, my favorite. If it has single bonds, if it has all single bonds, it's a tetrahedral. If carbon with one double bond, it's trigonal planar. Carbon with a triple bond, that'll be linear. So when I look at this figure, I look at that central carbon, I notice it has all single bonds, and I know that's going to be in that really super strong tetrahedral shape with all the angles at 109.5. This is that goat head shape that we've always referred to. This will be in letter E. '29. SF2. So S will be our central atom. We have F on each side with its valence shell electrons. And we make some simple single bonds. Now, a first guess would be like, man, these must be linear. Look at it, it's all in a line. I have a single bonds all the way through. We have to remember we have these large electron domain clouds here. Those balloons are going to push things away. They're going to push this way. They're also going to push each other away. And by doing that, we create a really unique structure. We'll have our sulfur in the middle. We'll have a fluorine going back out of the screen, another fluorine coming toward us in the front of the screen. That angle is pretty much set, and then we have these two electron domains out here. This is like the tetrahedral's third cousin twice removed. This is the bent structure out of tetrahedral. And that will be answer D. We know it's this weird bent out of this AB2 formation because these electron domains are going to repel each other. Another similar example for this bent structure is water. If you have oxygens and hydrogens, here's our bent structure for water. Same formation. Cool. Last but not least, 30. You got carbon. What is a tetrahedral? Well, it's got 4 bonds, and they all have the same angle, 109.5 degrees. And remember, this dark piece is coming out toward us. This piece away, we can make this methane. The dotted lines are pulling back out of the screen, and then the H's are in the screen, our X and Y axis. There we go, and that would be answer D as well. So, lots of stuff in this video. Let me know if you have any questions. This video goes from 16 all the way through 30. So as far as this study guide is probably your best resource for the final. I'm going to use more or less the same questions. I might take a few out or add a few here and there, but I'll scramble up the answers and scramble up the questions. But this is your main study guide for the final exam. So, miss you guys. I hope you're doing well. I look forward to next semester. I think this will be really fun. Have a great afternoon.